the beginning of chapter 3 at least is going to go into some probability and area models. So hopefully you remember that from integrated 1, obviously. Some of that we've already done. So long story short, probability, what we're really looking at is we're going to try and figure out how many outcomes we're looking for and divide that by the total number of outcomes. So what I mean by that is, let's say we're talking about flipping a coin and trying to get it to land on heads. Well, there's only one side of that coin that is a heads, and there's two sides of the coins altogether, right? So the probability of flipping a coin and getting a head is 1 out of 2. So that's really what we're talking about as far as outcomes we're looking for. We were looking for a head. There's only one head. Total outcomes, well, the total outcomes was a head or a tail, so there was 2 outcomes. So it definitely gets more complicated than that, but that's just sort of a easy way to start with what we're looking at here. So there's a couple different ways that we're going to be breaking down information. One of them is a systematic list where you literally, let's say we're talking about rolling 2 dice, right? The first dice might be a 1. It might be a 2. It might be a 3. So this is like the first number is the first die, and the second number is the second die, right? So the first one could be a 1 and the second one might be a 1. Or the first one might be a 1 and the second one might be a 2, and so on. Or maybe the first one is a 4 and the second one is a 3. Or maybe the first one's a 6 and the second one's a 5. The long story short is we're going to list every single possibility, and that's a systematic list. Maybe we want to make a tree diagram. Right? The first roll could be a 1, 2, 3, 4, 5, or 6. And it doesn't matter what you get on the first roll. The second roll might be a 1, 2, 3, 4, 5, or 6. Right? And so if I end up on this branch right here, that means the first roll was a 5. Uh-oh. That wasn't intended to happen. Okay, so that would mean the first roll was a 5 and the second roll was a 4. If I end up right here, that means, well, let's say right here, the first roll was a 3, the second roll was a 3. If I end up right here, the first roll was a 2, the second roll was a 6. Or we might actually see an area model, right, where this is going to be our first roll, is a 1, 2, 3, 4, 5, or 6, and this is our second roll, 1, 2, 3, 4, 5, or 6, and this is the odds of, something happening here, right? If we get a 5 and a 1, we get a 6. If we get a 4 and a 2, we get a 6. If we get a 4 and a 4, we get an 8. So these are different ways of representing the exact same information. You'll know there's 36 ways to roll 2 dice here. There's 6, 12, 18, 24, 30, 36 ways to roll 2 dice here. And there are 6 by 6, there's 36 ways to roll 2 dice here. So it shouldn't really matter which way we're looking at. The odds are going to be the same. It's just our preference of how we want to write these things out. So to jump into this, we're going to today start with an area model. So this will be the one that we're dealing with today. In previous courses, you studied probability, which is a measure of the chance that a particular event will occur. In this section, you solve probability problems that require you to analyze more complicated situations of chance. The next 2 lessons focus on tools for listing all the possible outcomes of a probability situation called the sample space. So the sample space is all the total things that can possibly happen. The sample space of flipping a coin is heads and tails. That's all the things that can happen. The sample space of rolling a dice is a 1, 2, 3, 4, 5, or 6 because that's all that can happen. So it's in the genes. Can you bend your thumb backwards at the middle joint to make an angle like the example right, or does your thumb remain straight? The ability to bend your thumb back is thought to rely on a single gene. What about your tongue? If you can roll your tongue into a U shape, you probably have a special gene that enables you to do this. Assume that half the U.S. population could bend their thumbs backwards and that half can roll their tongues. Also assume that these genes are independent. In other words, having one gene does not affect whether or not you have the other. And randomly distributed. That means it's spread out through the entire population. Then the sample space of these genetic traits can be organized in a table like the one below. And I want to make a couple points here where it says assume that these are independent. Well, not all things are independent, right? Let's say we took your odds of being 6'5" or taller and your odds of having a shoe size over 12. Well, there's a probably, if you're over 6'5", you probably have a shoe size that's over 12. right? So it's not random. It's not like, one of one and one of the other. This, we're going to say one doesn't affect the other. Whereas if you're 6'5", it probably doesn't affect your shoe size. So just worth considering. So according to this table, what is the probability that a randomly selected person from the U.S. has both traits? Well, that is, what's the chance that he or she can roll his tongue and bend his or her thumb back? Well, if we look here, can you bend your thumb? There's a 1 in 2 chance here. Can you roll your tongue? There's a 1 in 2 chance here. So we need to multiply the numerators. 1 times 1 is 1. And we're going to multiply the denominators. 2 times 2 is 4. So there's a 1 in 4 chance that you can bend your thumb and roll your tongue. There is a 1 in 4 chance that you can't bend your thumb, but you can roll your tongue. Hopefully we're seeing how we read these tables. If you're in this box, that's a no for bend thumb, but that's a yes for roll tongue. If I'm in this box, there's a 1 in 4 chance that I can bend my thumb and I cannot roll my tongue. And there's a 1 in 4 chance that I can't do either, according to this 50-50 table. So it says, what's the probability that a person has only one of these special traits? Well, this person has one of the special traits of rolling tongue, but not the other. This person has one of the special traits, bending thumb, but not rolling tongue. So a quarter plus a quarter would be a half. So we said this one was a quarter. There's a 1 in 4 chance of being able to do both, but there's a 1 in 2 chance of having one or the other. It's more inclusive, so the odds of that happening are better. So this table is useful because every cell in the table is equally likely. Therefore, each possible outcome, such as being able to bend your thumb but not roll your tongue, has a 1 in 4 probability. However, this table assumes that half the population can bend their thumbs backwards, but in reality, only a quarter of the U.S. population can bend their thumbs backwards, and 3/4 cannot. It also turns out that a lot more than half, about 7 of 10, can roll their tongues. How can this table be adjusted to represent these percentages? Discuss this with your team and be prepared to share your ideas. So hopefully you're already thinking about what it should look like. I'm going to go ahead and, oh good, it looks like they have already done this for us, but hopefully we recognize we just need to change some of these numbers, right? So what we would do here is we would change these statistics, change these odds a little bit, and we would refill in the table. So that might look something like this. We said, oh, what happened? I thought I erased everything. Let me pause this and erase this stuff. Well, and it reflects the numbers they gave us. 1 in 4 can bend their thumb, 3 in 4 can't. 7 in 10 can roll their tongue, 3 in 10 can't. I'm still going to do the same thing. So it's going to be 7 out of 40 here. It's going to be 21 out of 40 here. It's going to be 3 out of 40 here. And it's going to be 9 out of 40 here. So hopefully we understand. Again, we're going to multiply the tops and multiply the bottoms. So if I ask 40 people, and I have big classes this year, so that's almost a class worth, I would expect 7 of people in class, if I had a class of 40, to be able to do both. I would expect a little more than half to be able to roll their tongue but not bend their thumb. Hardly anybody would be able to bend their thumb but not roll their tongue. And about a quarter of the people wouldn't be able to do either. So that's what this table would look like if we change those odds. And you can see how different that is than the half-half. All right, I'm going to pause it and set up the next. Present a sample space that has outcomes that are not equally likely is by using a probability area model. And this is kind of a cool way. An area model uses a large square with an area of 1. The square is subdivided into smaller pieces to represent all possible outcomes of the sample space. The area for each outcome is the probability that the outcome will occur. So for example, if 1/4 of the population can bend their thumbs backward, then the column representing this ability should take only 1/4 of the width. So you can see it's much narrower. And what we're going to do is we're going to get a kind of an actual look at roughly what it would look like. So when we roll the tongue, if you'll remember, we said it was like a yes was like 7/10 and a no was like 3/10, right? So if we were to do that, it might look something like this. And now you can see visually how this thing breaks out into the more likely things have a bigger box and the less likely things have a smaller. It's so small I can barely write 3 out of 40 there, right? And that would be 9 out of 40. So you can see if we do a probability area model, it sort of gives us a quick visualization of what's most likely and what's least likely. So kind of interesting. So it says, how can the diagram be altered to show 7/10? Well, we already did this. The areas of the regions represent the relative probabilities for different outcomes. For example, the portion of the probability area model representing people with both special traits is a rectangle with a width of a quarter and a height of 7/10, like we had right there. What is the area of this rectangle? We said it was 7/40. What does the area mean in terms of the two traits? That means that they can roll their tongue and bend their thumb. It says, what is the probability that a randomly selected person can roll his or her tongue? So yes, they can roll his or her tongue, but not bend their thumb. It's 21 out of 40. And again, it says, show how you got it. Well, we multiplied 7 times 3, and we multiplied 10 times 4, and we know that it's a little bit more than half, and you can see it's a pretty large box there. Alrighty, so probabilities in vain. This is this one's not too bad. The next one gets pretty dark pretty quickly. So probabilities in vain. You and your best friend may not only look different, you may also have different types of blood. For instance, members of the American Navajo population could be classified into 2 groups. 73% have type O, 27% have type A. Blood types describe certain chemicals called antigens that are found in a person's blood. So you can ask Mr. A or whoever your biology teacher is about this stuff, because I don't know anything about it. So suppose you select 2 Navajo individuals at random. What's the probabilities for types O and A for the 2 individuals? This time, drawing an area model that is exactly to scale would be challenging. A probability area model like the one above is still useful because it allows you to calculate the individual areas even without drawing it to scale. Copy and complete this generic probability area model. So we could do it as fractions, but this one I think I'm actually going to do as decimals. 73 over 100 is 0.73 and 27 over 100 is 0.27. So that's what I'll do. I will grab my calculator and I will just do that math. 0.73 times 0.73. I'm going to get, and you could call it 0.5329. Hopefully we know if we move the decimal 2 places, that's 53.29%, right? These 2 boxes are going to be the same size because it's 0.27 times 0.73 and 0.27 times 0.73, so only need to do this once. And we're going to get 19.71%, or 0.971. And then finally, I could just subtract 100% minus, but I think it's going to be faster to go 0.27 times 0.27. Should be somewhere around 0.06 or something. There we go. 0.0729, I think it was. 7.29%. Let's go ahead and verify that. Yeah. Okay, good. So it says, suppose you select 2 Navajo individuals at random. What are the probabilities for types O and A for the 2 individuals? Well, they both get O is 53.29%. They both get A is 7.29%. This time, okay, so what's the probability that 2 Navajo individuals selected at random have type A? We said it was 7.29%, so it's pretty unlikely they would both have A. What's the probability that they have the same blood type? Well, this is a different question, right? This question, there's a chance they both have O, and there's a chance they both have A. So I have to add those together, and I'm going to get 60.58%. So 60.58% they have both the same, but only 7.29 that they have type A. All right, I'm going to pause again and set up the rest of it. Book throws a curveball at us and asks us just a kind of a dark question, and here we are. Shipwrecked. Zach and Nick, both from Vermont, are shipwrecked on a desert island. Zach has been injured and is losing blood rapidly, and Nick is the only person around to give him a transfusion. Unlike the Navajo you learned of in problem 3-3, most populations can be classified into 4 blood types, O, A, B, and AB. In Vermont, approximately 45% of the people have type O, 40% have type A, 11% have type B, and 4% have type AB. While there are other types of other ways in which people's blood can differ, this problem only considers these 4 blood types. So make a probability area model representing the blood types in this problem. List Nick's possible blood types along the top. So there we go, Nick's there, and Zach's here. And again, this is going to be like 0.45, 0.4, 0.11, and 0.04. So there's some shortcuts that we can take here, and we will take them. So 0.45 times 0.45 is 20.25%. And just for clarity's sake, I'm just going to write the percents. I'm going to ignore the decimals, so hopefully you're fine with that. Now I want you to see something here. We're going to end up getting like this pattern that goes diagonally because we end up multiplying the same numbers over and over. So it should sort of help us reuse some of these numbers. So I'll show you what I mean real quickly. So this one is going to be 0.45 times 0.4. So 0.45 times 0.4. I'm going to get 18% here. But I'm also going to get 0.45 times 0.4. I'm also going to get 18% here. So it's the same math. 0.11 times 0.45. I'm going to get 4.95%. But I also have 45 times 11 here. I'm going to have 4.95% there as well. And so on and so forth. So now I'll go 0.4 times 0.4. I think that's only going to appear once. I think it's going to be 16%. I don't know why I did the math on that. Now we'll go 4 times 0.45. So 0.45 times 0.04. I'm going to get, that's only 1.8%. And that's going to be 1.8% as well. So hopefully you see what I'm talking about here as far as the shortcut. 0.4 times 0.11. I'm going to get 4.4%. My wife just got home, so I'm going to pause this video for a second. All right, so I'm sure you're sick of watching me multiply. I went ahead and filled in the rest of that table as well. All right, so it says, what's the probability that Zach and Nick have the same blood type? Well, they could both have O. They could both have A. They could both have B. And unlikely, but they could both have AB. That's less than a 1% chance of that happening, right? So I got to add those all together. I am going to get, I don't know if I can move this out of the way far enough. So 20.25 plus 16 plus 1.21 plus 0.16. I'm going to get 37.62%. There's a 37.62% that they have the same blood type. It says, luckily, 2 people do not have to have the same blood type for the receiver of blood to survive a transfusion. Other combinations will also work, as shown in the diagram at right. So O can donate to everybody, but can only receive from O. B can donate to B or AB. AB can accept from anyone. So hopefully we see how this table works. It says, assuming that their blood is compatible in other ways, a donor with type O blood can donate to receivers with these lists here, type O, A, B, AB, etc. While the donor with blood type A can donate to A or AB, a donor with B, like we said, how this table works. It says, assuming that Nick's blood type is compatible with Zach's in other ways, determine the probability that he has a type of blood that can save Zach's life. Well, first of all, there's a 45% chance that Nick has type O, and if he does, he can save his life. But I want you to think about what saving his life would entail. What is he going to grab bamboo shoots and jam them into each other's veins and let it trickle through the chute into the vein? It just seems unlikely that this is going to end well for Zach, if you understand what I'm saying, but no reason to think too much about it. Well, let's pretend Nick, so again, I guess here's what I'm saying. let's go with the color like this. If he has O, if Nick has O, I can add up all these percents. Well, I don't need to add up all these percents because I already know it adds up to 45. If he has A, well, he's got a 16% chance here, but also this 1.6% chance there. So there's a 17.6% chance he could save his life if he's got A. Well, what if Nick has B? These two right here. So if he's got B, not looking fabulous for Zach, I got to be honest, but 1.21 plus 0.44 is going to be a 1.65%. That's another 1.65% chance. And then if he's got AB, not looking good if he's got AB. Probably not going to end well. Anywho, if I add all these things up, I get 45 plus 17.6 plus 1.65 plus 0.16. I'm going to have a 64.41% chance. That's assuming that you give him credit for being able to like essentially do the surgery as well. But I hope you get what the book is getting at, that there's sort of like if then. If Nick has this, then he can donate. If he has this, then he can donate here. If he has this, then he can donate here. If he has this, he can only donate here. So the odds change, but what we're saying is they all count until we know what type of blood Nick has. All right, it says you made a critical assumption in problem 3-4 when you made a probability area model and multiplied the probabilities. Blood type is affected by genetic inheritance. What if Zach and Nick were related to each other? What if they were brothers or father and son? How could that affect the possible outcomes? Well, maybe family are more likely to have a certain blood type, so maybe those odds would go up tremendously. Maybe they both have O or both have A or both have B just because they're related. And it says, what has to be true in order to assume a probability area model will give an accurate theoretical probability? Well, there's a lot that we have to assume. First of all, we have to assume that he can even jam the bamboo shoot into his vein like we talked about. But, that the numbers are correct, that there's not some, like I said, the shoe example that we used earlier, that, we're not talking to a bunch of Mr. Heflins when we talk about, if you don't know Mr. Heflin is, he's a tall guy. He's probably got big feet versus me. I'm not the tallest guy in the world and I don't have big feet, right? So if we're talking about those shoe size things, we want to know, are we talking to tall people? If we're talking to all Swedish people, that might be one thing versus, I don't know, maybe another country where they have shorter people. Those are just the kinds of things that could possibly affect probability. I think I'm about done with this one.